derivatives. In these sets of videos, I introduce the concept of a tangent line to a point on a continuous smooth curve, the slopes of those tangent lines, and the derivative. We're going to use the slope of secant lines to approximate the slope of the tangent lines, and also we'll be using the concept of limits. I'll be appealing to your intuition as I discuss the ideas, so my language is not always perfectly precise or accurate, as I am trying to give you a feel for these concepts. In the second video, you'll see the formal definitions for the slope of a tangent line and the derivative of a function. So the ideas presented up to that point are to help you see why the definitions make sense. This is a video especially for Joey and Kira. It's an introduction to derivative, and here are some basic ideas we have to understand. First of all, a line tangent to a curve at a certain point. Well, what does that mean? Let's say we have some curve. This black curve is some function, right? And we would like to find the tangent line to the curve at a certain point. So I have 4 points here. The first one over here, this blue point, well, what do I mean by that tangent line? I mean something like this. That might be the tangent line. It just touches the curve right at that point. Now, this is approximate. That's not exactly the correct line. I'm just eyeballing it. We're getting as close as we can. All right, I have another one over here. I have a green point, and it looks like the tangent line is something like this. Notice the tangent line looks like it has a slope of about 0, where this first one it looks like the slope is maybe -1. All right, let's take this red point. This looks like it may be something like that. Again, that looks like about of a slope 1, just approximating. And here's another one. This looks more shallow. So maybe that's a slope of, -1/2 or something like that. So first of all, we have to get the idea of what it means for a line to be tangent to a curve at a certain point. So this is just a basic idea. At this point, it's important to note the following. The graph or the curve, which could be a line as long as it's not a vertical line, so it has to be a function. The graph has to be smooth and continuous on both sides of the point in order for the graph or the curve to have a tangent line at that point. All right, so what I mean is, see how this is a nice continuous curve? We'll be able to pick points and find tangent lines at that point. As long as it's continuous, so what I mean is on both sides. If you look sort of to the right or the left, it's still part of the curve. And furthermore, there's only one tangent line at any of these points on the curve. It may look like, well, you could draw another tangent line. So here's an example. You say, hey, I think this looks like a tangent line. And that's the problem, is that we need to be a little bit more precise to find exactly where it is. We're just eyeballing it right now. Okay, so let's get rid of this. Okay, so for instance, if you have some sort of curve like this, and then it goes and stops, this is not continuous at that point or at this point where it stops. It's not continuous, but all these other points in between, you're going to be able to find tangent lines. Secondly, you can't have something with sharp curves like this. So here's places where you would not be able to talk about the tangent line. But all of the rest of the places on the curve are fine. All right, now we're going to go on. The key to finding the tangent line is to find the slope of the tangent line to the curve at that point. So imagine you could find the slope, for instance, of this red line, and you knew what this point was. Well, once you have a slope and a point, you could use the slope point formula and find the equation of the line. And as it turns out, using limits and algebra, we're actually able to find the exact slope of the tangent point. The slope of the tangent line to the curve at a certain point, or at least for some curves. So we're going to be working on that, And that leads us to the definition of a derivative. So isn't that exciting? All right, so the key is defining the tangent line. So let's take the graph y equals x squared minus 3, which is a parabola, right? But remember, when you're talking about functions, y is the same thing as f of x. So if we were going to write this in function notation, f of x equals x squared minus 3. And when you write an ordered pair, you're used to writing xy, right? But using function notation, we could write x f of x. So these are some things to just keep in mind, some notational information. All right, this is a rough sketch of this parabola, f of x equals x squared minus 3. So you can see the various points it goes through. Let's just look at the very bottom, the minimum value here. And if we were going to draw the tangent line, that looks like it's just going to be straight across. And in fact, that is the exact tangent line. This is the tangent line at the point 0, negative 3. And you can tell the slope is m equals 0. Now, that's by eyeballing it, and we can prove it later, but for right now, hopefully that looks like the slope is 0 to you. Now, let's take another point and see what will we do to try to figure out some, the value at some other place. For instance, what if I wanted to know the slope here at 1, negative 2? I'm not really sure. You can't, when you eyeball it, you can't tell for sure what that slope is, right? So this is just a rough idea, but it looks like it's going to be positive, that's for sure, right? And it looks like it's going to be steeper than 1. So the goal here is to find out the slope of that tangent line at the point 1, negative 2. So we're going to try to figure out, find the slope of the tangent line at 1, negative 2. One technique is to approximate it. So you could look at it and you could maybe give an approximate idea. Maybe it's a slope of 1.5, 3 halves. Maybe it's a slope 2. It's hard to tell because I'm not really graphing that line perfectly because this is just a sketch. So one technique is to draw what's called the secant line. All right, so what is a secant line? The secant line is a line passing through 2 points on a curve. All right, keep in mind, this was the graph of y equals f of x, right, which was x squared minus 3. Okay, so we're doing f of x equals x squared minus 3. And this would be a secant line. It's just going through 2 points of the curve. Now, that is certainly not going to be the tangent line, correct? But I can figure out the slope between these 2 points. So let's just do that. How would you figure out the slope of this red line? You would have a difference, the difference quotient here, so you'd have one ordered pair, the y over x, and the other ordered pair, y over x. And that's going to give you negative 2 plus 3 over 1, which is 1. So the slope of this line happens to be 1. And obviously, that's not as steep as the real tangent line. So let's say we were trying to get a little bit closer. What about if I tried to get closer and I figured out, what if I chose that for my other point? So I would have to figure out what ordered pair that is. I do know the y value is 1/2, and you'd have to plug in 1/2 into the function. F of x equals x squared minus 3, and if you put in 1/2, for x, you get 1/4 minus 3, which is minus 2 3/4. Okay, so this is 1 minus 2 3/4. Okay, you can see it's much closer down to negative 3. So I could get maybe a little bit better approximation if I used the point 1, negative 2, and 1/2, negative 2 3/4. Let's try that. If you take those 2 ordered pairs, 1, negative 2, and 1/2, negative 2 3/4, you would have, again, I'm going to do this one first. Let's see. I'll put this in the top. Negative 2 over the positive 1, and negative 2 3/4 over 1/2, right? This is plus plus. So I have 2 3/4 minus 2. That's just going to be 3/4 in the numerator, divided by 1 minus 1/2, which is 1/2. And then you multiply by the reciprocal. And that gives us 3/2. All right, so you see how it's getting a little bit steeper if I were doing this line right here. Still not the exact tangent line.